Okay. So the topic this week is a new topic, and it's about decision trees. And this is one of the methods which we could call, or one of the less complicated mathematical methods. It is a method which is intuitive, and a decision tree itself is something which you can think of like the game you would play when you were on a long car drive with your parents when you were a kid, and you had these 20 questions. Have you played that game? So some of you would think of something. It could be an animal, it could be an object, and so on. And then you had 20 questions in which you should try to guess whether this was a cat or dog, and so on. And the answers were typically yes, no. I guess everybody here has played that game when you were a kid. And a decision tree is very much like that. Now, a decision tree, as you will see, is a very simple method to implement. We are going to look at the way we can write the algorithm. And for many of you, this becomes also an interesting topic for the final project, because you can write a code for decision tree, and you can use that as a basic element for more complicated methods. And as you can see from the title of the lectures this week, there's something which is called ensemble methods. Now, ensemble methods is a collection of trees, essentially. And these trees are easy to train. And the ensemble methods, you can think of that as a collection of trees. And one of these typical collections of trees is called a random forest. And these are very popular methods which have been extremely successful in both classification and regression problems. And you will see that a decision tree is a kind of white box. It's not a black box. It's a white box. It's something which is easy to explain, and you can actually bring it to even people who are not very familiar with what is going on. So it's a method which can be implemented quickly, both for classification and regression cases. And one thing which I wanted to show you here in the very beginning is a simple case where we can encode a decision tree. So I just wanted to show you an example here where we have given as a data random walks for a given number of steps. And then we are trying to make a polynomial fit with a polynomial of degree 2 and a polynomial of degree 10, as you can see here. And we want to fit these random walks. Then we can fit these random walks with a decision tree. So if we run this code here, so let's do that. And running that code gives us, if we now look at it here, it gives us a result when we now are making a polynomial regression case. You see this, the green lines here are the random walks. So we're just putting lines between random positions, which have just been drawn. And we are trying to fit a second order polynomial and a 10th order polynomial to that. So this is not very successful. And being not very successful, okay, this means that the result you get are so-and-so, as you might expect. A decision tree, on the other hand, is actually something where you can now fit the points. So the points are now these dots, which you see, the data. This is just a random walk. And we can make decision trees of different depths. I'm coming back to what the depth means. The depth means a parameter. So you see now when I make a tree of a depth 7, I can actually go through quite many of the points. I can change this if I go back to the code which you have here. And the way we would do this now is to use us in scikit-learn. We have a library for decision trees, and this is for regression case. And one of the parameters you would specify would be the max depth of the tree. So if we now make a max depth of, let's say, we increase that one or decrease it to 7. So we make it more shallow, the tree, and I will come back to what that means. What you will see then is something which looks like this. And now you see you're missing more of the points. I can make the tree deeper. And we will, as I said, we will come back to what that means. So suppose I make the tree of a depth equal to 13. And when you now look at it, you see that my tree, this is no longer max depth is 7, it's actually 13. You see now that my pink line is actually going through essentially all the data points. So I'm training a model which reproduces all data points. Now, if I were to include this on a test case, the model I've trained, I would quickly enter the region of overfitting. So a decision tree in general is a model which is extremely easy to train, but it can easily lead to overfitting. As you can see here, what I've done now is to train a tree which goes through all the data points. And I'm going to try to explain to you how we actually train the tree so that you can go through all data points. So one potential problem with decision trees is the overfitting case. However, they are very simple to program and implement. The codes which you see here are taken from the library scikit-learn. And in scikit-learn, the only thing you would need then is simply to include this for this regression cases. You have a linear model, which we have been using here. And then if you go down here, we import the decision tree regressor. If you're dealing with a classification problem, you would have the decision tree classifier. So decision trees work easily for classification problems and for regression problems. So let's try to demystify what these trees are. There's also another thing which is very nice with decision trees. So if we go back to the beginning of these lecture notes here, just right after this example, you can present a tree in a very easy way. So let me just show you. I should have an image here. Let me just see. Where did that image? No, that disappeared here. So let me just go back. Today is not my day here. So if I look at the decision tree, it typically looks like this. So this is applied to the cancer data. Now, a tree is set up in the following way. So you have a root node here. So that's the root of the tree. And that is seemingly the most important feature. And from that feature, you see now that you can have a true false. And it tells you how many true and false values you have. And the next feature is the worst concave points. And the other one is the worst texture. This is the Wisconsin cancer data, which you studied in project 2. And you see now you can actually go down the tree and you can see which features are the most important one gradually as you move on. So this is a way by which you intuitively can present the results of the model which you have trained. And then you can present this to people and say, this is what the model gives us. And we can understand the basic features of that specific model in terms of these and these properties. So it's something which becomes intuitive, and it also functions as a building block in many of the more advanced models. So if you look at a model which is called bagging, which you actually assemble many trees, then you can both improve the overfitting problem, which you have with a single tree, and you can actually do pretty well on predicting properties of systems. Actually, these methods, which are based on decision tree, where the decision tree is a so-called simple model, which you use as input to more advanced models, give extremely good results for, in particular, classification problem. And one of the methods which has been extremely successful is called gradient boosting. And gradient boosting, there's a library which is built on that, which is called extreme gradient boosting. This is just a highly efficient library which implements a gradient boosting method, which uses a decision tree as what we normally call a weak learner. That means a simple method which we can keep improving upon. So in essence, what you end up doing is to build up a forest of trees. And there are different methods. One is random forests. Another one is based on boosting methods. Essentially, these are ensembles of trees where the algorithm or program for making one tree enters as the simple first approximation. So what we are going to need to do now is actually to demystify what these trees actually are. In order to do so, let's switch to the whiteboard before we go back to the main Jupyter notebook again. So why should we do decision trees? Now, decision trees, as I said, they function as a simple building block in more advanced methods, which you can see as collections of trees. So one thing, it's simple. It becomes a very useful building block in ensemble methods. And these ensemble methods, there are some popular ones, and the names are always a little bit amusing in the beginning. So bagging. So bagging is actually a set of decision trees based on bootstrap. So the AGG stands for aggregation. So this is bootstrap aggregation of decision trees. So we're simply putting together many trees and we're making a forest. And we use the bootstrap method to train these trees. So bagging is one of the methods you will encounter, and that is also extremely simple to program. The other method which we're going to encounter, which is also widely popular, is a random forest. So the distinction between a random forest and bagging is that a random forest, we try to use a random selections of features to grow a tree. So the bagging method would start with trees which are always lookalikes. It means that if you have a fir tree, you will have a wood of fir trees. So if you have 500 decision trees, they will essentially all have the same root properties. A random forest, on the other hand, if you take the cancer data, which you discussed in project number 2, instead of growing a tree on all 30 features, you pick randomly only 10 of them, and then you grow a tree. And then you pick randomly again, new 10 features, and grow a new tree, which will be different. And in that way, you can reduce both this overfitting problem and also problems with variance and other statistical properties which are unwanted. So a random forest method is, if you think of it now, when you have developed an algorithm for a tree, you can actually make different types of trees and grow a way to make a classification or regression problem, which is extremely powerful. And then we have the boosting methods, where you use a decision tree as normally what we would call a weak learner. And then we have the final method, which has been extremely successful and been winning competitions in particular in classification problems. And that is gradient boosting. So these are the methods which we will cover through the rest of the semester. And some of these are actually very easy to implement numerically yourself. So if you think that is interesting for project number 3, this is one possible path. Also, people have, as one possibility, studied overfitting and the bias variance trade-off with different decision tree methods. That's also another option for project number 3. But these are things which we can discuss during the lab sessions. Now, let's look at a simple decision tree and the way it is set up. and then we are going to go a little bit deeper and set up the algorithm for a decision tree, because that is the basic building block in many of these other methods. So a simple tree, the way we set it up is first we need to find the root node. So we need to find some specific feature which is a dominating one. And we are going to look at an example later on grades which people get, whether you are above or below the average. And we are going to look at features like the grade trend which people have, the hours you studied, and the hours you sleep. This is just a kind of fake data which you could make up, or you could actually do such measurement over a semester. And most likely your intuition would say that whether you get a grade above or below the average is something which is strongly correlated with a trend you had. So if you have a trend where your grades are above average, it's not unlikely that for that specific exam, your grade would be above average. So that is probably a feature which will be the dominating one, as you will see from the example which we are going to work on a little bit later today. So the root node collects the essential feature, and so let's just set it up. That's normally the essential feature of a data set. And you saw from that cancer data set that there was something which was called the worst perimeter. And since I'm not a pathologist, I cannot tell you what that means. But that comes out from the training as the most important feature of the system. So that means that when you're making a kind of overall assessment of a data set, you would say, this is the most important thing to look at. And after that, there is a new feature you should look at. So the way you build up the tree then is often as a binary selection process. This is the most common case. So you would then find, and this is the easiest one to train actually. So you would then set up true or false. And then you would find a certain number of outcomes which are true and false. And then you would continue like this. And this is normally called an interior node, or just a branch of the tree. So we keep this kind of tree naming. So you would often see this as either interior node or as a branch. And then you continue like this. And then you have new true and new false. Then we have a new true, a new false, and this continues till the final point. And this goes on to what we might call the final points. And I'm just writing it like this, and these are called the leaves. So if you think of a tree, you start with the root of the tree, and then you build up all the different branches, and then you end up with the leaves of the tree. And these leaves, they contain typically only one class. So we would say that these leaves are pure in the sense that there is no admixture of other classes. So only one feature. So I'm using this classification language because that's a little bit easier to understand when we are looking at the setup of a decision tree here. And what we say then is that this case here is a pure case. So with pure case means that if you're having many classes, like the 30 classes we have for the cancer data, at the end, there is only one class which determines that specific leaf. So let's now look at in more detail at some specific examples so that we can understand a little better what these things actually mean. So when I said this pure, we have to define what is an impurity. So when we say that if all elements belong to the same class in one of these branches or interior nodes or the leaves, then we say that it is a pure class. So when all elements of a specific branch, because if that is the case, this becomes equal to a leaf in the tree. When all elements of a branch contain only one class, we say we have a pure case. What we call a pure case. So if the node is pure, that means that there is the probability of finding an object there is actually given by a specific probability, but we need a kind of measure of defining when the class is pure. So the question now is, how can we define a measure for when a class is pure? So there is no admixture of any other classes in that specific case. So there are, if all the training, so when we say a class is, or a leaf is pure or branch is pure, it means that all the training cases we are looking at, they belong only to one specific class. In order to develop your intuition about this, it's useful to look at a binary problem. And the standard and most traditional ways by which we actually measure whether it's pure or not is given by something which is called the Gini factor or the entropy. So there are two ways to measure this. And this is given by something which is called the Gini factor, which I'm just going to call for G. And the other one is the entropy. And you may have encountered the definition of the entropy, or either in physics, or if you do information theory, you may have encountered something which is called the entropy of information. So we call this for S. And both these quantities, G and S, they take values which typically lie between 0 and 1. So what we are going to say is that when G or S, when G is equal to 0, that is going to be a measure of a pure case. Similarly, when S is equal to 0, that is a measure of a pure case. So let's now look at a simple example. And we are going to look at an example which is a so-called binary case. So we have two probabilities. So we have the probability for true has probability which is equal to just a number p. And p is a probability, so that lives between 0 and 1. So if we have 0 probability, then obviously we have 0 probability. And then if we have probability 1, that means that there's 100% probability of being true, okay? So, and then it means that the false, if we think of that one, so false, since we only have a binary case, so false must be 1 minus p. And if we sum up the two of them, we have a total probability equal to 1. So that means that if I sum up the two cases which I have, I equal 1 up to 2 of the probability P of I. This is going to be 1 minus P plus P, and that gives us 1. So the sum of probabilities is equal to 1, as expected. Now, if we now look at these measures, one of the things we often want as a criterion for these measures is the following. For G or S, so the Gini factor or the entropy, is something which we could call the information content of a system, of a specific system, or just the degree of what we might call surprise. So how can we measure the information content of a given system which we're looking at? So we have some requirements which are often used. So measure of information. So one of the properties which we want to have is that it is additive. We also want this to be a continuous function. We want it to be non-negative. And often what we want is that the measure of this information is high for unlikely events. And one of the measures which is widely used is this entropy. So let's look at the entropy. So the entropy is defined as this quantity S, which is minus, and then I have the probability of a given event. So we can put an I here, multiplied with log. Now you can define the base you want. That will just give you a scaling factor. So we are going to take log 2 because we have only 2 events. So this is just only going to scale the maximum value. Now, if you think of the entropy now, if you look at this function which you have here, if you plot this, if you just take log of 2 of P of I, that quantity is, if we now plot this as a function of P of I, we know that the maximum value is 1, and then we have the minimum value 0. So this is a function which is non-negative because it's going to look like this. That is minus log if you plot it. So if we go back to these properties we had, it is non-negative, as you can see here. It is a continuous function, as you can also see from the log, except when you go to 0. So that is a problem. It is additive, and the additivity, you can see that if this P of I represents the probability of 2 events, x1 and x2, then if I do that, if these are independent and identically distributed variables, then what you get is that you get minus log 2 of P of x1 minus log 2 of P of x2. So this is the additivity, which is normally reflected in the fact that many of the events we are looking at are independent and identically distributed. Now, another thing you see that if we have the maximum probability, if we go back to this, we want this quantity to be high for unlikely events. You see now that if I have max probability 1, that means 1, that is a pure case. There's only one thing happening. Then the measure for that one should be 0. Whereas if I have a high, it should be high for unlikely events. Then, so you see now that when I'm here, this is just probability is equal to 1. And then my log function is equal to 0 in that case. However, I have a problem with the behavior here. So when people came up with this information entropy, you see now that if I take this form on the other hand, if I take that and we look at this binary system, what we see then is the following. So let's just do the mathematics and look at what we get for the binary case. So we have S is equal to minus, and now we sum over the two probabilities from P of I of log 2 of P of I. So what we get then, and just keep in mind that 0 times log 2 of 0 is actually equal to 0. Then if we write this out, we will get now P of log 2 of P minus 1 minus P of log 2 of 1 minus P. So I'm just putting in, so this is the true case, and this is the false case. So these are the only two probabilities which we have. So what you see now, when it's true or false, so S is equal to 0 if P is equal to 0, so that is false. That means that there is only one possibility, right? So that's the pure case. So read this, when we are going back to trees, this is the pure case. Then if I take S is equal to 0, if P is equal to 1, that is a true case. So that is also pure. And the other thing which you see now, if I set up P equal to 0.5, then this entropy has its maximum value equal to 1. In that case, I have a mixture of both true and false. This is the same as us setting up a random case, in this particular case with true and false, where we have an equal likelihood for having it true or false, which means essentially that the likelihood for finding the system in a specific state is the one I would get by tossing a coin. So what I want to be able to is to classify a pure case, which contains only one class, in this case, either false or true. And then you see now that the maximum value is given by the case where a probability of 0.5, which then corresponds to, if I make a plot now of this system, what I'm going to get, if I make the plot here, I plot it as a function of probability. So I have either 0, 1. And in those cases, when I had 0 and 1, it's just 0. And then I have 1 here as a maximum value. And this corresponds to 0.5. And my curve is going to look something like this. So the maximum entropy, max entropy, when we just have a random selection of state, when coin tossing prevails. So it's equally likelihood to get true or false. So then we have a total mixture of all the possibilities. Whereas when the entropy is 0, as you can see down here, then it's either false or it's true. So there's only one class. Whereas here we have a clean admixture of both cases, true and false together. And it doesn't matter whether we pick one or the other one. So if we are making a classification problem and we have a case like this one, you could equally well toss the coin. So your tree then is going to look like, for this specific case, you will then have a root node and just simply something which splits in false and true. Now, if you now look at the P equals 0 case, that is the max entropy. So if we just write this down, if we take P equals 0.5, that corresponds to max entropy. And then we're going to take a small break after this. So that's the max entropy case. And that is the probability of an imperfect classification. Both cases are equally probable. Both cases are equally probable. And that is also what we called a measure of the most unlikely event. Now, another widely used measure is this Gini factor. And this is something which we will now take up after the break. So the other measure which is used when you build a decision tree is this quantity which is called the Gini factor. So you probably heard about the Gini factor when it comes to measurements in economy of economic inequality. So this is not exactly the same. This is another way of finding a function which measures the degree of unlikelihood. So if it's very likely, we want to have this factor G equal to the entropy equal to 0. So that means that that measures that we have a pure case. And then if we have mixtures or more unlikely cases where we have many features which are mixed together, we would like to have that as a measure of unlikelihood. So let's bring up this Gini factor, which is another quantity which is used in constructing a decision tree. So the Gini factor has a simpler expression. So let's just set it up. So this G is defined as a sum over I equal 1. This is the number of probability which we have, and up to the number of cases. So I'm just going to put this in terms of a letter M here. And then we have a P of I of 1 minus P of I. And this is the same as P of I, and I'm skipping the summation signs, minus I equal I, sorry, not that one. And then we have P of I squared. And since we know that the first quantity, this is the sum over all the probabilities. So if you look back at the case with the two classes which we had before the break, this true and false, we know that that sums up to 1. So the sum of the probability is always equal to 1 if we have normalized everything properly. So this quantity here becomes simply 1 minus this I equal 1 up to the number of classes which we have, which are just labeled with this M here. And this is a P of I. So this is just a measure, and you want the same requirement as we had before, that G should be something which now runs between 0 and some maximum value, which could be, say, 1 or smaller. So if you look at the specific case which we had here, for the simple example, or a simple example, if we do that, then what we get now is obviously that this Gini factor is equal to 1 minus, and if we take now I equal 1 up to 2, the two specific cases we were dealing with, either true or false, this becomes 1 minus, and we remember that the true case was just simply P squared, and then we have minus 1 minus P squared. That was the other one, the false case. So these were the two probabilities which we had. And then if we collect this, this becomes equal to 2P of 1 minus P. And then we see now that if P is equal to 0, then what we get is that this G is equal to 0. And if P is equal to 1, then this G is equal to 0. So this is like the entropy. Now, you may ask, how did people come up with these quantities? Now, they came up with these quantities based on the definitions of being continuous. We want this to be additive. We want this to be non-negative. And we want them to be constrained between some specific values where 0 is going now to represent the case where we have a pure system, only one class, like with the entropy. So if you have then probability of 1, either true or false, just 1, then clearly what happens then is that when we take log of 1, that is equal to 0. When we construct the Gini factor, we want to have the same kind of behavior as we had for the entropy, so that the most likely case with just one class gives us 0, and then the unlikely case gives us the maximum value. So it's a measure of unlikeliness or unlikelihood. And the case now when we take P equal 0.5, which is the same as just tossing a coin, we just have a complete mix of the true and false cases. In that specific case, what we see now is that this Gini factor is equal to 0.5. However, if we plot it, if we go back to that plot of the entropy, what you will see then is that it has much the same mathematical form as the entropy for that case here. So if I take the Gini factor now, this is going to have a max value of 0.5, and it's going to look something like this. So this is our Gini factor for the same type of system. So the most unlikely case is now given by the maximum value of the Gini factor. So these are measures which we often use as a handy way to convey the degree of probability. So you can think of the entropy as you having cooked up a measure for the degree of probability, where you simply want the maximum value of the entropy to be the one which represents the most unlikely case. Now, these are ways by which we are going to use to construct a tree. So let's now look at a data set and try to think of how we could make a code to find a decision tree. So the data set which I'm going to set up now is just a data set I made up on the fly here. And what we are going to do now is to make a classification problem as follows. So this is a classification example. And when you are making or deciding which is the most important feature for the final grade, so this is a classification problem based on 3 features, and where we want to figure out or make a model which allows us to predict whether you will get a grade above average or below average. And we are going to have 3 features. One is your trend based on previous courses. The next one is the number of hours you studied. And the third one is the number of hours you slept while you were studying this specific course. And then we want to figure out which is the most important feature, because then we can tell you that based on these and these properties, we can predict whether you will get a grade above the average or below the average. Does that sound reasonable? So this is just a case we are making up, but it could be a relevant case where we try to find correlations in order to see what are the features which can let you guys get a better grade in a specific course. Do you need to sleep more or sleep less? Yes. Yeah, the most. Say again. That is what we are going to do now. So the question for those of you online is that we want to find a root node with the most important feature, the one we should focus on if we want to get a better grade. And then the question is, how do we find it? So the way we find it is to use this entropy or the Gini factor as a measure to decide which is the most important feature. And this is how we build up the algorithm for decision tree. So let's show how we can do that. So the example which we are going to use now is an example where we have the following features, or we can call them attributes. You will see that as a name in the literature as well. And the kind of feature we are going to look at is the grade trend. And we are going to look at this in a gross way, whether this is above or below. We are going to look at the number of hours we studied. And we are going to say this, we classify this in the same way, so we can have high or low, so just two properties. And then we are going to look at the number of hours we slept. And we are not going to say anything about what is high and what is low. So this is a very gross way of splitting the data, okay? And then the thing we want to have as an output, so the features are the inputs, like we did with the cancer data, and the output is also a binary case, and that is a grade, the final grade, above or below average. So this is the data set which we are going to look at, and now we are going to figure out from the decision tree which is the most important feature. And we are going to make a data set which now looks as follows. So I'm just going to switch here, if that is okay. So I'm going to make a table. So I'm going to just call the first one for trend. And then the next one is study. So that's the number of hours we study. And then we said sleep. And the final one is the grade, whether that is above or below the average. And we're going to take 10 entries here. So these are just numbers which I've made up. So when I set an 1 here or above, so I'm going to have above average, and then I have below. And now I'm just going to use A and B as above or below, if that is okay, okay? So that means I'm going to have an above here, the next entry point, an above. There's going to be a below here, and then there's going to be an above, and then I have below, below, and then I'm going to have an above. So let me see. I'm going, yes, and then I have a above and an above here. And then the next one, we are going to have a low. So that is a low number of hours. And the next case, we have a high. So I'm just going to relabel this as low and high with an H and an L. So the next case is an L, and then I have an H, and then I have low, low, and then I have high, high, and then I have a low. Let me see now if I did this correctly here. High, low, low, high. Sorry, this is supposed to be a low one, and this is a low one, and this is a high. Then the next one, I have a high here, I have a low here, so I sleep too little, L, and then I have a high, high. So this is a data set which I just made up. There is nothing scientific with the data set which you see here. It's simply me putting in, not exactly randomly, but almost randomly, high, low, and so on. So this is just something I made up. However, what you will see is that I made it up so that the grade you get at the course is strongly correlated with the trend which you had before you took that specific course. So I have made the data in a specific way. but there is nothing scientific behind the collection of this data set. It just serves as an example to find the way we can make the decision tree. So here I have a grade above, and then here I have a grade below, and then I have above, and then I have a below, and then the next one is a below, and below, below, and below, and the final one is above here. So I have 4 cases above and 6 cases below. So now we want to find the Gini factor. In order to make the tree. So that means we want to find the property which is most likely. So the decision tree is going to be dominated now by the trend or the property which has the strongest impact on the final grade. A tree. So let's now look at the P, and that is the trend is equal to above. So A for above. So what we see then is that we have 6 divided by 10. So we have 10 cases. If you go back to the table here, if you do the counting, you have 1, 2, 3, 4, 5, 6. So that's the probability. And then I take the probability of the trend below. So now what I'm doing is I'm calculating the Gini factor for each of these features in order to find the one which has the smallest Gini factor. So remember now that high Gini factor means high degree of unlikelihood. Small Gini factor means that this property here is pretty pure. So we use the Gini factor to find out which is the most important feature. It doesn't need to mean that that Gini factor, the root, is equal to 0. There's another reason for why many people take the Gini factor. And one of the reasons for that is that the entropy requires calculating the log of a function. And the Gini factor is thus a little bit quicker to calculate, especially if you have lots of data sets. So, but whether you use the entropy or the Gini factor, normally you get basically the same result for a tree. So let's now look at the for the trend here. And then what we need to do now is to look at if trend is above and grade is below. If I then go into the table, what I will see then, if I count the number of cases, then what I get is that this probability is equal to 2 divided by 6, 1/3. So trend above and grade below, I have 2 cases out of 6. Okay, so what I'm doing now, I'm going back to the table and I find the case where the grade is above and where the trend now, or the grade is below and the trend is above. So I have 6 cases and only 2 of those have a grade which is below. Then I go to the next case, and if I say that if the trend is above, if past trend is above and the final grade is below, to do that one, what we find is a probability of 4 divided by 6. So that means that if I now take the trend above, I fix the trend above, and then I look at the grade. No, sorry, that should be, I wrote below here, it should be above. Sorry for that. Then, if I look at this one, then the Gini factor for that specific case, and you could do the same thing with the entropy, is then 1 minus, and then I have 4 divided by 6, and this is squared, plus 2 divided by 6, and this is squared, and that is equal to 0.45. But then I have to look at the next case. If trend is below and grade above. And if I look at the table then, I will find that this P is simply equal to 0. And if trend is below and grade is below, if I do that one, what I will see that this is P equal to 4 divided by 4, which is equal to 1. So that means that the Gini index for this specific case is just 1 minus 1 squared plus 0 squared. So this is equal to 0. Then I need to do a weighted sum for trend, where I multiply the probabilities. So I have a weighted sum for the trend. So then I take the probability of 6 divided by 10. I multiply with this Gini factor, 0.45, plus 4 divided by 10, multiplied by the Gini factor of 0, and that becomes equal to 0.27. So I take the probabilities for finding the overall case, and then I weight them by the Gini factor. Now, the way you build a decision tree is that you run through all the cases you have. So I'm doing this feature, I calculate the Gini factor for that specific feature. Then I go to the next one. So I will repeat. You see the basic pattern here? It's simply just you counting the number of probabilities. And then what I'm doing next now is simply to rerun these calculations for the Gini hours. So the Gini factor for the hours slept. So what I will find when I run the calculation, so I hope you don't get offended if I don't run through the calculations again, because it's exactly the same trend. I look at the number of hours slept and grade above and below, and then whether it's high or low. And if I do the calculations then, you are going to get a Gini factor, which is 0.47. So this means that the Gini factor 0.47 is close to 0.5. So from this data set which I made, the number of hours you sleep doesn't matter very much for the final grade, whether it's high or below. Probably you would have to make a bigger fine-tuning if you wanted to find some influence of the number of hours slept. Okay, so now I just said high and low without saying what is high and low. So this is a very, how to say, it's a rough data set, but the whole idea with it is to show you how you're going to build the tree now. And then you can repeat the same for the hours you studied. And if I do that, so this is the weighted factor. And then we have the weighted factor for hours studied. And in that case, we're going to get a Gini factor of 0.34. So that means that when I collect everything, you see now that the number of hours studied has a smaller Gini factor than the hour of numbers we slept. But the one which has definitely the smallest Gini factor is the number of, it's actually the trend, which we would have expected. So if you have a trend where your grade is above average, it is pretty likely that the final grade in a new exam will also be above average. That sounds reasonable, right? So what we would say then, when we have this, is that if we collect all this data, the root node is now going to be like this. So we will have the general trend, or what we call the grade trend, as the most important feature. And you would write a Gini factor of 0.27. If you use the entropy, you would have to write the entropy. And in this case, we are now making branches that if the trend is true, so, or trend above, we had 6 cases. And in the trend above, we have this result, and then we have the trend below. So that is below average. And if you look back into the original table, we had 4 cases then. So we split them between trend above and trend below. And in the trend below, we get the following box, which we need to split further. So if we now look at the left-hand side, so let's put question marks in here. And let's just simply label this as a left-hand side. And this is our right-hand side. Okay? So the left-hand side then, if we now break it down, it's going to look like this. So the left-hand side, so we're going to have a box here. So this is the grade. So I'm just going to use a G here to indicate that that's the grade. And if I plug in the grade, there's going to be above, 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 and then there is a below, there is a below, and there is a final above here. So that's the grade. That's the one we want to make a prediction of. Then we are going to look at the trend, which I write as a T here. And you know that all the trends are now above. So that means that the trends is something which we are not going to care about, right? Because we have already done that. So I'm just going to mark it like this because this is done. So what you see is that the decision tree is just a way by which we reduce the features. So we are not going to make an analysis of the trend again because we did that. So now we have singled out a case where the trend is pure. So we have only above, right? And there's no point in analyzing that one. But now we want to see whether the number of hours we studied or the number of hours we slept is more important for the final grade. So what we are going to do then is to make a new analysis. And what you see then is that we are breaking down the number of data entries for every branch which we make. So we get now a slept. So the first one is the number of hours we slept. And then the next one is the number of hours we studied. So let's just write sleep here. And then this one is study. So if we take the data set which we had, this is below, below, and then we have a high. And this is below, and then here we have a high number of hours slept. Here we have a high number of hours studied, high, and L, and high. And now we want to find out which one of these features are the most important factor. So what we are going to see then is the following. So I'm not going to repeat the calculations because the kind of calculations here are actually much the same. So what you would do, if you look at this one, you would now find first the P, the probability of sleep, equal to high. And you see you have, in this specific case, you have 2 cases only. So you have that case and that case. So here we have 2 divided by 6. And then you take the number of sleep, high, low. And that is equal to 4 divided by 6. And then I can now look at the possibilities, the different Gini factors. So if I calculate now the Gini factors, so what I need to set up is if high and grade above, then what I get is a probability of 1 if high and grade below. And if you look at that table, what you will see then is that this has a probability equal to 0. And if I continue like this, I will find that the weighted Gini factor for hours slept, so weighted Gini. So let me just, where did I have it? Yeah, so the weighted Gini, when I do the same calculations as I did before, weighted Gini for hours slept is equal to 0.33. Then I can repeat the same exercise for the number of hours we have studied, weighted Gini for hours studied. Then what I will find is that G is actually equal to 0 in that case. So that means that for that one, the most important feature is the number of hours studied. Then, if I go to the right-hand side of my internal branch, which we have, so if we go back to this one, let's see what that one looks like. So if we now break that one down, what we will see is that the right-hand side is going to look as follows. So we have a trend where the grade is below. We have a sleep, and then we have study, and then we have the grade. This is the output which we want to have. And in this case, we have a trend which is below, obviously, in all 4 cases. We have number of hours slept, high, low here. And then we have low, and then we have high, and high, and high. But then the final grade here is just always below. And the final grade is actually the one we want to classify. So that means that there is no point in doing anything here, because you will find that the Gini indices for all these cases are just 0. So the final grade is below. So we actually stop there, because we know that if your trend is below, the final grade is below. So that branch actually stops there. So it means that the tree, if we now look at the final tree here, is going to look as follows. So we will have a root node where we have the trend as the dominating feature, and we have a Gini index of 0.27, and you have 6, 4. So you have here above. Whereas here, if the trend is below, the grade is also below. That's the data set which I set up. And we need to remind ourselves again that this is an example which I just made up, okay? So there's nothing scientific. When I put in these features with their specific values, I just made up these values, okay? So this happens, in my case here, that the trend, when the trend is below, then the final grade is below. So the final output. If we now, so this is the final leaf. So this is the leaf, and that internal branch becomes actually the final point. So we have 4 cases which have a trend below, which also give a final grade which is below. So that stops there. But then here, what I find now is that the one which has the best result is actually the case when the number of hours slept is the one which gives the best result here. So, no, sorry, the hours studied. So hours studied. And in that case, it has a Gini factor of 0. And this specific branch, the internal node here, that splits into a new node, which then looks as follows. So we have above, this is the final grade, above here. So what we have is 4 cases which have the grade above. So there are 4 here. So this is final grade, which is above. The grade above. And then I have 2 cases where the final grade is below, final below. So what we see now for this simple example, when we have calculated this Gini factor, and you would have to do this repeatedly again and again, when you are depending on the number of features you have, you first run through all the possible features. You find the dominating feature, and that defines the root node, which is this one. When you've done that one, you separate things into smaller classes. So the class where we were above gave us this table. And then from this table, we have to recalculate the Gini factor for the features which have been left. And in that case, we have only these 2 features left. And the same applies here for the right-hand side, except that now the final output is the same. So the final output is, in this case, just given by a grade below. And that means that that internal branch becomes the leaf, the final part. Whereas the case which we have to the left-hand side, we need to figure out whether the number of hours we study is more important than the number of hours we sleep. And we would have expected that to be the case. So actually, when I made up this data, I put in that bias towards the number of hours you study, which in a certain sense, we would expect, right? So keep again in mind that this is not a scientific collection of data. It's just me making them up in order to demonstrate how you can make the tree. So the alternative to calculating the Gini factor, if you want to do that, is to calculate the entropy. And you would use that one as well as a measure of the most unlikely case. So you want to have a pure selection. So when you now look at the final leaves here, this is a pure one. It has only grades below. This is also a pure one because it had only grades above. And this was also a pure one because it has only grades below. So the final leaf, the final point of a tree, is a pure case. There is no other classes which enter that one. But the intermediate ones can actually have many different cases. Yeah?
I think the data set was a bit different. You can have mixed cases.
Oh yeah,
And then
exactly. So when I made up this data case, it was simply to show that even if you have several features left, you end up with just a pure case for the final result, which you're looking after. But you see the recipe, right? So it means that you need to traverse all the data sets. And then you traverse all the data sets, and then you keep reducing till you have a final point where there's only one result left. In our case, it's the grade either below or above. So we made this separation. And this is something you can then tell people that, hey, I went through all this data, and then I found that the trend is the one which correlates best with the final grade. And after the trend, the second most important feature is the number of hours we have studied. So a tree, as you see it like this one, is a very intuitive way of actually explaining your data. And it can, it's often not misleading, but it can actually be very helpful in analyzing a data set. And that's why trees are so popular. However, a tree can easily lead to overfitting because you can make the tree deeper and deeper. And let me explain to you that through the next type of applications. So, and this is a regression tree. So what does that mean? So a regression tree is us trying to fit some kind of continuous function. So how can we use that to fit numbers? So like we did in project number 1 and also in project number 2 when we try to fit a polynomial. So we want to use a tree when we have trained it to make predictions. So what we can do then is now to think of setting up our data set as follows. So let's just look at the regression case. And suppose now that we have two variables, x1 and x2, and then we have a set of observations. Oh, these are just numbers, right? So when we have, I'm just gonna write these different numbers, and I'm just gonna put some dots in here. So these are just numbers which we have, and they can mean different things. But let's suppose now that we split the region into different, the whole region into different smaller regions. So we have a V and a W. And then we call this first region for region 1, and then region 2 here. And then we have a region 4 and a region 3. So the way we would do the classification here is as follows. So we could now, when we look at these different regions, we could now say the following. Suppose now that the most important feature is that if x is less than v, so that's the most important node, suppose we find that, then if that is equal to that, we can go to either R1 or R2. Here, if that is true, this is what happens. If it's false, then we can go to R2 or R4. And then I need to make a new test here. Then if x2 is less than w, and here we have also the same test we need to make. If x2 is less than w, what happens then if it's true? Then we are in R1. If it's false, we end up in R3. No, sorry, sorry, that should be R3 here. Then if we go back to the image which we made, so we have if it's true, if it's smaller or equal than W, we end up either in R3 or in R1 or R2 or R4. So that means that if it's true, I just put a T here now, then we end up in the final region R2 or R4. Now comes the important thing when you're dealing with a regression case. So in a regression case, the prediction is equal to the average value in a region Ri. So if I have 4 values in that specific region, like you saw here, the prediction I'm going to make is going to be the average. So these x's represent different function values as input of x1 and x2. So the x's you see here are then different function values, which I just plugged in here. So in this particular case, you would take these 4 values and calculate the average of them. And that is a prediction you make. So if we now call this for x1, x2, x3, and x4, that means the prediction for R1. So your prediction X for R1 is simply 1 divided by 4 of X1 plus X2 plus X3 plus X4. So in principle, this should be different from the X's I have. So I'm just going to put tilde here, like that. So this is my prediction. So think of these X's you see in the small regions as function values, which we want to make the predictions of. And then as values of X1 and X2, we now find the average. What this means is that you can keep making this region smaller and smaller. That means that you make the tree deeper and deeper. So the tree here is actually an opposite tree because you start with a root and then you go down. So when we say a deep tree, that is the same as a high tree. So a deep tree means that you can now make these regions smaller and smaller. So you just think of now you could now split this one into this one again, if you wanted to, right? And then you have only two values. So you could now have a region R5 and R6. And when you have R5 and R6, then you can make this region again smaller and smaller. So you could do this. And then finally, you would nail this down to this specific value here only. And then you see that if you do that, you can really overfit your problem. Because then you make a perfect fit to the data points which you have. So if somebody then gives you something outside what you did fit in the training, then you may actually fail miserably. And you saw that from the case we had before the break, when we run through these random numbers, we could actually make the tree deeper and deeper, which means that at the end, you can then decide that in a specific region, there is only one data point. So you can really nail it down, and that makes a very deep tree. And the deep tree, as you can see, means also that you do many, many more splits. So it takes more time to train it. What we are going to do next week, when we start discussing these methods like ensemble methods, etc., and boosting methods, is that we are just going to use a shallow tree as a weak learner. And then we are going to have methods to improve upon that by starting with a simpler tree, which requires less cycles to train. And then you will see that through these ensemble methods, we can improve the quality of the training by aggregating different trees. And this is the whole recipe behind random forests, bagging methods, and boosting methods, where you actually use a more shallow tree, because as just one tree, you can make a perfect training, but then you will overfit without any problems. Because then you have nailed down a model which simply now contains, let's say, only one or two few data points in that specific region. So next week, we are going to generalize this with a decision tree, and we are going to make models for bagging, boosting, etc. And then we will have a final lecture, which is actually not, you've probably seen that there is a small error in the general schedule. So the final lecture is actually November the 25th. Also, we will have the lab open the first week in December, if people want to just come by and use the lab. Okay, I'm going to stop here. And then next week, we are going to use the decision trees, because hopefully now you see the way we make the trees. We are going to formalize it, set up the final algorithms. And one of the most used one is called the CART algorithm, which stands for Classification and Regression Tree. And it's essentially built upon these ideas we have discussed today, where you use either the Gini factor or the entropy to split the trees and make the tree. And then you can decide how deep the tree should be. The deeper, the more cycles you need, and the more likely you are to overfit, because then you make a training to perfection. But you see the intuitive aspect of the trees, and the mathematics here is not very difficult at all. It's simply you making a search and calculating these quantities like the Gini factor and the entropy. Okay, we're going to stop here, and then at the lab, feel free to propose, by the way, feel free to propose alternative variants of project 3. And we are just going to continue discussing the projects. Okay, feel free to ask questions or whatever you might like to ask about.